What the heck? Or you guys, well, all right. Your screen. All right. So, all right. How's everyone doing? Anyone have any questions about anything? Can you guys see me Zoom, folks? Everything fine?
Yep.
Can you see the other screen?
Where it's showing the steps, or
Like this? You see the circle thing I just drew?
yeah.
Everything's showing.
All right, good. How about my in-person students? You guys doing all right? Everything? All right, everyone's good. I'm actually excited about today's lecture. I always like this one. So, and like, I mean, of course, I love chemistry. I also like puzzles, like solving puzzles, and like this is just like, if you look at Lewis structures like another puzzle. If you see it as something that you like work on and it's kind of fun, other than if you think of it like, oh gosh, it's chemistry and I don't understand chemistry, it's all math and I hate this, then you're not going to enjoy it. But if you think of it as kind of like little puzzles, it gets to be a lot of fun. So working on Lewis structures, and this is where we left off. This is how you write it. You write down the skeleton. And for this class, the skeleton, the center atom is going to be the biggest and or least electronegative atom, like almost always. But I'll show you, well, we can go through a couple of examples. Sum up the valence electrons of the outside electrons. You count them going left to right on the periodic table. You put octets on the outside of the on the outside, and you add double and triple bonds as needed. And the last step, minimize formal charge. And if there is going to be a negative one, you put the negative charge on the electronegative atoms, because those are the ones that tend to draw electron density. So let's talk about formal charge. So formal charge is, this is a way of sorting out where electrons are and where electrons are not. So we already talked about oxidation states. So we mentioned oxidation states, and then oxidation states, with positive and negative, that's way in different bonding molecules and or ions. That's a way of keeping track of where electrons are and where electrons are not. Formal charge is another way of doing it, and it's looking at specifically Lewis structures. And the way that you determine the formal charge, each atom gets half of the bonding electrons plus all of the lone pairs, and then you compare that to the original number of valence. So for dinitrogen here, so each nitrogen has 3 bonds and 1 lone pair. So that means that the dinitrogen gets 1 electron from each of the bonds. So 1, 2, 3 from the bonds. It has 2 from the lone pair. So each nitrogen atom has 5 electrons. Nitrogen starts off with 5 electrons. So how do I know that? Because the periodic table, and 1, 2, 3, 4, 5. So nitrogen there. 1, 2, 3, 4, 5. Can we lose somebody? Okay, so, and since nitrogen starts off with 5 and it has 5 electrons, its formal charge is 0. So let me try this with a different example. I should probably just erase this. I can start over. Rather than have it be pretty. So we have this structure OCN minus, and we have a couple Lewis structures. The first one here, A, we have oxygen, single bond with a carbon, triple bond and a nitrogen, whole thing negative charged. B, we have oxygen double bond with a carbon, double bond with nitrogen, and C, oxygen triple bond with a carbon, single bonded to nitrogen. So let's look at the formal charge for each. So for starting out with oxygen, oxygen has 6 lone pairs. Let me make this smaller. Lone pairs, and then bonding electrons. It has 6 from lone pairs, 7 from bonding electrons. I'm sorry, 1. 6 from a lone pair, 1. It starts off with 6. It has 7. The formal charge on oxygen is -1. So you get this. Does everyone understand this for this specific oxygen? It has 6 electrons to start off with. Oxygen is 6 in the 6 valence in the periodic table. For the formal charge, it has 7 electrons, 1 bonding, 6 lone pairs. So it has 7. It starts with 6. Its formal charge is -1. Does everyone understand this? Yeah, it has 1 more electron than to start off with. So make sense? So carbon is pretty easy. It's got 4 bonding, no lone pairs. So 0 lone pairs, 4 bonding. Carbon starts with 4. It has 4. Its formal charge is 0. And then nitrogen. No, wait, I did yellow for nitrogen. So nitrogen here has 3 bonding, 2 lone pairs, 2 lone pairs, 3 bonding. It has 5 electrons. It starts with 5 electrons. Its formal charge is 0. So anybody have any questions with that so far? All right, so move on to this oxygen. This oxygen has 4 from the lone pair, 2 from bonding. So 4 lone pair, 2 bonding. It's got 6 electrons. It starts with 6 electrons. Its formal charge is 0. Carbon has no lone pairs, 4 bonding. It had started with 4 electrons. Its formal charge is 0. The nitrogen has 2 bonding and 4 lone pairs. 4 lone pairs, 2 bonding. It started with 5. It has 6. Its formal charge is -1. Yes.
Will you have a formal charge of the same charge of the whole molecule? Like at least like it's
You can,
negative?
yeah. Well, yeah. Oh, you mean the sum of the formal charge will equal the charge of the,
Of the molecule.
yeah,
Okay. Gotcha.
and or ion. That's a good point. Then oxygen here, 2 lone pair, 3 bonding. So 2 lone pair, 3 bonding. It has 5. It starts with 6. Its formal charge is +1. Then for carbon, 4 bonds, no lone pairs. Its formal charge is 0. That one's easy. Nitrogen has, 1 bonding, 6 lone pair, 1 bonding. It has 7, starts with 6. Its formal charge is -2. So, all right, so we have 3 different Lewis structures. And so first of all, minimize formal charge. This one has a -2 in it. That's not minimization, right? That's the maximization. That's wrong. So now we have to choose between A and B. And so which one is it going to be? Is it going to be the -1 charge on the oxygen atom or the -1 charge on the nitrogen atom? Then you look to see the electronegativity. Electronegativity, oxygen has a higher electronegativity than nitrogen. So you can either look in the chart or you can go by the periodic table. What am I doing there? Jeez. You can go to the periodic table. And right, so electronegativity, it's trend higher to the right and higher up. So oxygen is further to the right than nitrogen. So the more electronegative atom is oxygen. That means that this one, I don't know, should I start it? This one here is the proper Lewis structure because The formal charge is on the most electronegative atom. So, does that make sense?
What if the formal charge is positive?
Then not have, then you would put it on the more electropositive or the least electronegative atom of the possible lower numbered Lewis structures, lower formal charge Lewis structures. Other questions? Okay. So let's see if you can figure this out. What is the formal charge on the central atom in ozone? And there's the Lewis structure for ozone there. So it starts off with 6. How many think A? 0. How many think B? +1. So that's the right answer. Almost everyone said +1. And if you look, you can kind of see that. I'll pick a brighter color. How's pink? Can you see pink? Yes, you can. Okay. So oxygen has 5 electrons, 3 bonding, 2 lone pair. So 5 electrons, it starts with 6. So that means it's going to be +1. So, make sense? Okay. All right. And so I told you I look forward to this because I get to draw Lewis structures today. It's fun. So here are the exceptions to the octet rule. So the first exception to the octet rule, we'll talk about our free radicals. So maybe you've heard the term free radicals before. Free radicals means an odd number of electrons. So starting with nitrogen monoxide. So skeleton's gonna be easy, it's a diatomic, right? So diatomic, there's only one choice. I can put oxygen on the other end, but it's the same molecule. And sum up the electrons. Nitrogen has 5, oxygen has 6. That means we have 11 electrons. So we place 2, 4, 6, 8, 10, 11. And so oxygen has an octet, nitrogen has 5 electrons. 5 electrons isn't really cool. Oops. So we'll put a double bond. Now oxygen has 8 electrons, nitrogen has 7. And so since that just 7 is close to an octet, so then we're just gonna leave it there. And then this is then the most proper Lewis structure for nitrogen monoxide. So, and nitrogen monoxide is an interesting substance. It has a very curious effect on half of the people in this classroom. Does anybody know what nitrogen monoxide has done in the human body besides blood vessel dilation? It's what causes human erections. So it's the levels of NO in your blood, specifically geared towards that. So
That's all what it is.
yeah, increases your NO in your blood. Yep. So, but as a gas, it causes actually nitrogen dioxide too. Nitrogen oxides, they're really noxious. You're not gonna, if we breathe them, it would not be pleasant. So I mean that's why you have things that increase it in your bloodstream. If you just breathe in nitrogen monoxide, you'd be coughing. That would be an interesting experience, I guess. Coughing with anyway. So I'm sure.
So what do you mean by free radicals?
Free radical means an odd number of electrons.
Oh, so then.
So
this
an odd-
happens during when there's odd number of electrons.
When there's an odd number of electrons, that's called a free radical.
Oh, okay. And then,
Yeah.
so then the bigger, the more like electronegative one will have the octet.
In this case, yeah, because oxygen is more electronegative than nitrogen. Thank you. I did not clarify that. Yes. Oxygen is
That's
more.
general, like for other rules as well, right?
Yeah, well, obviously, if you look at the formal charge, so we can then go back to the formal charge. If you look at nitrogen, Nitrogen has 1, 2, 3, 4, 5 electrons. It starts with 5 electrons. This formal charge is 0. Right, so formal charge of everything in this molecule is 0. So this is definitely, when you, that's the other hint. If you get a formal charge of all the atoms being 0, you've written a good Lewis structure. So
So it's just gotta be as like 0 as possible, guys. Just
it's almost always 0, to be honest with you.
The bond, yeah, the bonds between them, that's basically 2. But you're only counting one end of the bond.
Which one are you talking about? I don't understand your question.
Like for oxygen, it's 1, 2, 3, 4, 5, 6 on its side, but it shares 2 others with nitrogen.
Yeah, don't forget though that this Lewis structure can be written.
Like that.
Yeah. I mean, we can write it like this. So you can see the nitrogen. I mean, we usually don't write it like that, but if you see, look at the bonds, nitrogen has 5 electrons, oxygen has 6. Right, but
But you would know like you wrote it right. If you
Yeah.
look like that.
yeah, the formal charge of each of these are 0. Because oxygen starts with 6, has 6, nitrogen starts with 5, has 5. Yep. Other questions? And then nitrogen dioxide, so 5 plus 6 times 2, right? Because there's a 2 here. So 12 plus 5 is 17 electrons. And then we put big atom in the center. And we place 4, 6, 8, 10, 12, 14, 16, 17. Again, oxygen has 2, 4, 5. And so we will then put a double bond there, and then you can have a resonance form then between the two. And if you count the if you count the actually, I'll put this single bond there. So although if you look at nitrogen has 4, the formal charge, nitrogen is always going to be, with formal charge, it's going to be +1, and then it's going to be -1 and 0 for that. There's not really any way to write this such that there's not a that you, well, I guess you could write it this way, where you have that, and then now you have that. So I guess that's another proper way, because then you would have the -1. I guess then, but then you would have,
Wouldn't it be 0?
yeah, that would be 0. But that's going to be a debatable one though, because you are ripping an electron away from a more electronegative atom. So, but I guess minimizing formal charge. No, I guess this is the right one. Yeah, this would be the right one then, because I'd minimize formal charge, that would put everything at 0. Yeah, okay. So then there would be a resonance form where this would be the other way around. Where you have this. Oops, no, wrong way. Wait a second. That's right. And it went away. There we go. So that would be the resonance form.
so is the Lewis equation gonna be pretty arguable in the testing case? Or is it-
No, there's gonna be easy ones.
Oh, but there's gonna be easy.
I mean, it's not gonna be,
Like, as in
it's not gonna be I might do expanded octet, but not free radicals.
Did you say it's also like not right for Lewis structure?
Lewis theory is wrong.
And that's why, because it can be written in so many ways. We just don't have-
it's wrong because it predicted properties incorrectly. Certain properties are predicted incorrectly with Lewis theory, and it's predicted properly with quantum mechanics and molecular orbital theory. So it's more like the theory provides, experiment decides that we have an experimental discrepancy. We'll talk about that next chapter, which we won't get till after Thanksgiving. So, other questions? But it's a very solid theory. Very, very solid theory. And that's why we still teach it. And so what? Why do we care? So it's one way that we can put out fires. So is anyone familiar with the best movie ever made, Terminator 2, Judgment Day? Oh, we got one good soul in this class. I don't know about the rest of you guys. I'm joking, of course. Do you remember when yeah, you remember that scene, huh? With the in the Cyberdyne systems when Arnold blows up the door and then the halons are going down, put out the fire. So what do halons do? Well, halons stop the chain reaction. So maybe have you heard of the fire triangle before? Has anyone heard of the fire triangle? Fire triangle is heat, oxygen, and fuel. So if you want to put out a fire, you get rid of one of those three: oxygen, heat, or fuel. So if you say you have a fire, and how do you put out the fire? Well, you can just let it burn and not put any, like you have a campfire and don't put any wood on it. All the fuel will be consumed, the fire will go out. If you have a smaller fire and like say you have a kitchen fire and it's like a grease fire, you take the lid and you put it on top of the pot. And then that will get rid of the oxygen and then that will put out the fire. Or if you have a campfire, only do this for a solid fire, a solid that's like wood, especially. But if you put water on a fire, what do you hear when you throw water on a fire? Yeah, your steam, and that's 40.7 kilojoules per mole. Actually, that's of heat. It's a lot of heat. So throwing water on fire takes away the heat and puts out the fire. So there's another one. Then later on, they came up the fire tetrahedron, where each face of a tetrahedron, and one of the faces of the tetrahedron was the chain reaction. And the chain reaction includes free radicals. So when you have a chemical reaction, that's a combustion reaction. So like here's a combustion reaction. I'm sorry, right? So it's not, you have an oxygen, an O2 and two hydrogens meet up and then bam, turns out two waters. They like the oxygen will come and rip off a hydrogen, it becomes an OH minus radical. So you can have you have O2 and it comes over to a hydrogen and it just rips off one of the hydrogens and now you have an OH radical. And then maybe you have two H radicals, maybe it rips it off and then you have an oxygen radical as well. And I'm just showing the one unpaired electron plus a hydrogen radical, and then those go and react with other things. So like actually chemical reactions when they happen are very, very chaotic. Okay, it's not neat and even. You have different steps, and the steps also involve like radicals forming, and then they go and they react with other things, and you don't always get all the same product. So in this chemical reaction, you might get hydrogen peroxide, for instance. So because you have just weird combinations happening and you get different products. So chemical reactions are just one shot thing. And you get and the intermediate steps always, well, they usually involve free radicals. So same thing with fires. So if I wanted to put out a fire, I can release something that sweeps and finds those free radicals. And the compounds that we have for that, they're referred to as halons. Anyone want to guess what family of elements are in halons?
7.
7. What is the name of group 7? Halogen, yes. Halons have halogens in them. So when you heat up halons, they release halogens. Halogens stop the chain reaction. They put out the fire.
Did you talk about this in this gas class?
I guess maybe, I'm not sure.
Okay, that sounds familiar, sorry.
Okay.
Because now that you, I think that you did that, I was like, okay, now it's gonna be.
Yeah. Was I there when you were?
I think so. Now,
Okay.
now I think so.
Yeah, what we're talking about, I was the science coach for Ms. Kasha Gan at Kamehameha, and I came to their classroom a few times. So
To do demonstrations on fire extinguishers.
no,
No.
I came like I think at least 3 times. So I taught a class. I thought I taught limiting reagents,
I
but
don't know, I missed half that class.
or maybe yeah, maybe Ms. Gahn did that. Well, she's no longer there. She moved to Seabury Academy. But yeah. Maybe. I'm not sure. I thought I did something else, but anyways.
Maybe it was the firefighters. I don't know.
Oh,
Because I
the fi-
remember them talking about the triangle, and stuff, or like somebody talked about the triangle.
Okay. It would make sense that firefighters would talk. Do you have firefighters come?
Yeah, isn't her husband a firefighter?
I don't know. I never met her husband.
No, I think he is. We had them come like once.
Yeah. Well, it would make sense that firefighters would talk about the fire triangle and tetrahedron. So, but yeah, no, at least I don't remember teaching that for your class. I thought I did limiting reagents, but that's okay. Who knows? Maybe it's the brain fog from the vaccine still. 3 weeks later, 2.5 weeks later. No, I'm just joking. So, but any other questions? Nope. Okay. So that's exceptions octet rule. There is the odd electrons. We have incomplete octets, and specifically the boron family. So group 3 tends to do this. And so if you look at boron trifluoride, for instance, so boron has 3 and fluorine has 7. So this is 24 electrons. So 3 times 7 is 21 plus 3 is 24 electrons. So boron's in the middle, and you have 3 fluorines. So 3 lines is 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Okay, so we placed all 24 electrons. I put in octets on the outside. And normal rules applied, you would mean that you would then put a double bond on boron, and then you would then do this as a resonance. But it turns out for boron is perfectly happy with an incomplete octet, and that does not have the resonance structure. It just sits here with its 6 electrons and it seems okay with it.
Is it because it's positive surrounded by negatives?
No, it's because boron's just kind of weird. Boron chemistry is really strange. So you can, this is outside the scope of this class, but you can have hydrogens that bond like such. And this is called a bridge bond. You can have hydrogen bonding with 2, and it forms this kind of weird sort of bridge bond with the other ones. So yeah, boron is just a weird element.
And everything, every element in its family too?
No, just boron. Well, aluminum will do a little bit. So, but boron just, like I said, it's really weird. It's a really hard element to melt too. It's got a really high melting point, which is which is also kind of strange how high the melting point is of boron. Because if you compare it to like, I mean, because like you look at like beryllium and lithium, it's really easy to melt those. You get to boron, it's just like huge freaking melting point. And then like nitrogen, carbon, yeah, but oxygen, not so much, nitrogen, not so much.
It has 24 electrons and that's divisible by 8. Is there no any way like the fluorines could just take all the electrons and boron be left with none?
Oh, I mean an ionic bond?
I guess.
Yeah. No, usually, no, it doesn't usually do that. Carbon will do that, which is weird, but boron won't. Boron tends to bond, even more so than carbon in a way. So that's a good question, but no, boron tends to form very covalent bonding networks, and it's when it bonds with itself, it just doesn't really form that many ionic compounds. I mean, you have like borate. You can have like boric acid and like what is that stuff called? Borax, the sodium borate. But I mean, that's boron covalently bonded to oxygens. So, but it doesn't tend to form its own ion that frequently. It likes to bond more. Like I said, carbon will actually form ions more readily than boron will. That's chemistry though, you know, like, I mean, it's not like, and I remember this is Lewis theory. It doesn't describe everything. It's just chemistry is observational science. And so we're reporting to you what's going on, you know, and so if it seems weird, it's because it is weird. And we're just trying our best to make sense of it. So, but remember there are exceptions. It's not my fault. So that's boron trifluoride. And here's aluminum trichloride. So aluminum trichloride, surprise, surprise, is going to look surprisingly similar. 3 plus 7 times 3 is 24 electrons. So same thing, aluminum, and it's going to form. So just like that, and then bonding all the way around, or lone pairs all the way around. So same thing. And maybe the next thing you're thinking of, like, wait a second, we have aluminum that's covalently bonded to a non-metal. Can we have metals bonding to non-metals covalently? And the answer is yes. So once again, something that, you know, I'll tell you a rule and then I teach you the wrong rule, or teach you how it's different. And where we're actually going, and well, where you're going is the reason why bonding happens is that you have a group of positive nuclei and electrons and they approach each other, and then the electronic and magnetic fields interact, and then the electron energy levels change. If the electron energy levels change such that they're lower energy than the original, then they will bond. So as aforementioned with the second law of thermodynamics, where it's more disorder to have lower energy and have the energy leave and then wreak havoc. So that's what's driving is probability, and then the electronic and magnetic fields of groups of atoms coming together. And we just have general things that we teach. And this is one of those rules in Lewis theory. Well, it started off with metals and non-metals, and we said, you know, metals and non-metals have ionic bonding, and now you can see that's not even the case. Actually, metals can covalently bond to other metals. They can bond to non-metals. Non-metals can covalently bond to themselves. They can form ions. And like I said, as we had the previous conversation with boron, some just don't like forming ions for whatever reason. Boron's one of them. So in carbon, like I said, carbon will form ions more readily than boron will. So, but that's why I think chemistry is cool though. So I can see, as a student though, I can see how it can be really confusing. So, the questions with this so far? No. Expanded octet. Oh, I didn't mention what this stuff is used for. Does anybody know what aluminum trichloride is used for?
Putting out fire.
No. Good guess though. It does have a hammer. What? Starting fires? Nope, not starting fires either. Has nothing to do with fire. Perhaps the color red.
The fire trucks.
The fire trucks. It stops, it causes blood clotting.
Oh, it causes it.
Yeah.
The same with boron, trichloride?
No, it doesn't do that much. We don't use it for much for anything. Aluminum trichloride, though, it's that's used to clot blood really fast. So like on emergency kits or surgery, like if some patient starts bleeding or soldier or something like that, you slap this on the wound, it'll clot the blood real quickly. So expanded octets. So this theory, at least with Lewis theory, which seems to correspond well with quantum mechanics, this only works for period 3 and above. And what's period 3? So hydrogen, helium is period 1, lithium and friends is period 2, sodium and friends is period 3. So phosphorus and sulfur here are in period 3. And so they can engage in expanded octets. Nitrogen and oxygen, these are period 2. Those tend not to have expanded octets. So, okay, let's look at this. So phosphorus trichloride. So phosphorus has 5 electrons, chlorine has 7 times 5. So this is going to be 40 electrons. So we put phosphorus in the center, and then we put chlorines around the phosphorus. So we've placed, we have 5 lines, that's 10 electrons, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. Okay. So now we've placed octets on all the outside chlorines, and phosphorus actually has 10 electrons around it. And so since it can have an expanded octet, it is totally fine with that. So in sulfur hexafluoride, it's the same idea. Sulfur has 6 electrons. Fluorine has 7 electrons times 6. 7 times 6 is 42 plus 6 is 48. 48 electrons. So put sulfur in the center. And then fluorines all the way around. So we placed 6 lines, that's 12 electrons, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42, 44, 46, 48. Okay, good. If I ever miscount, I'm like, oh crap. So this is sulfur hexafluoride. And if you've noticed, I've actually drawn them in a certain way. You'll find out next chapter that the structure for phosphorus pentachloride, this is going to be trigonal bipyramidal, such that you have a 3-sided pyramid and 2 of them on top of each other. And sulfur hexafluoride is an octahedron where you have like 2 square pyramids on top of each other.
Is that having to do with the orbitals?
Yes. Yes, it does.
And also, you have an expanded octet because S&P orbitals equals 10.
S&P orbitals equals 8. You have to have empty d orbitals. You'll find out next chapter that this is sp3d. This is sp3d2. So you have the orbits hybridize. That phosphorus engages in bonding with 3 of its atomic. Oh, I'm sorry. 5 of its atomic orbitals, and sulfur will engage with 6 of its atomic orbitals. With the theory, but the theory is also wrong.
It's gonna leave college.
You're gonna leave college now? Hey, don't say I didn't tell you.
No, but it's not.
Hey, you're the one that sent me the mathematical thing. So,
Why there's exceptions to this one, like the constant exception.
well, what causes the exception is because it's lower energy. But if you go by the theory says that for periods 3 and beyond, the empty d orbitals can hybridize, and then you can go beyond 8. Octet rule comes from the 2 electrons in the s orbitals and the 6 electrons in the p, right? 2 plus 6 is 8. So with period 3, though, n equals 3, you also have L equals 2, so which are D, and then you have for phosphorus and sulfur here, this is the principal quantum number 3, right? This is 3s and 3p, but since it has the principal quantum number 2 also has the 3 Ds, and then the Ds can then engage in bonding even if they're empty. They can be occupied by extra electrons that chlorine and or fluorine provide, or whatever it is they're bonding with.
So why would we have to connect that to this? So like, how would you come up with that?
Come up with what?
What would we look at? Or how do we relate the D part? Now I guess why is more, but. Oh,
I was answering a question. We haven't learned about that yet until next chapter.
Oh,
The D, you find that out next chapter when we talk about, sorry, I have a problem where if someone asks me a question, I give a $1 answer to a nickel question. And so I will answer as completely as possible. It comes from a theory called hybridization of orbitals, which again is linked to Lewis theory, and it works most of the time. And it actually is fairly consistent with what we see with quantum mechanics, but it's generally, like I said before, you'll find out it's wrong. So
when we go across expanded, like when we're trying to make expanded Lewis models, and like, are we required to come up with this?
you'll be given something like PCl5, so or PF5 or something like that. And I mean, obviously, from this, there's an expanded octet because there's 5 things bonded to phosphorus.
Yeah.
So it's one of those, it's kind of like, you just kind of have to, well, from the problem there and doing it, it's going to be, I should say, it's relatively obvious, if that makes sense. Because I think I would think it's obvious because it's not, you have 5 things attached to it rather than 4.
Oh, okay. So everything above period 3 or 3 and above, it can expand to 10 because of the d orbital.
Yeah, it can. It doesn't mean that it will.
Okay, which just depends on like, so but if it can, it will, right?
If it's low energy, then it will. I'm not giving you exact answers. It's because it depends,
Okay.
right? Because chemistry is very contextual.
Yeah.
So I mean dichloride, right? That does not have an expanded octet, and chlorine is period 3, right? So it doesn't mean that you're just going to always have an expanded octet for everything, but chlorine can have an expanded octet.
How many electrons does phosphorus start with?
5, nitrogen. It's nitrogen family.
Yeah.
Sulfur's oxygen family. So nitrogen, phosphorus 5, oxygen, sulfur 6. What's what?
Chlorine.
Fluorine, chlorine, yep. Oh, actually, maybe I can go here. Let me show you. Is it going to be sulfur? Do they do it fluorine? Oh, here we go. Here's sulfur. Here's sulfur hexafluoride. So Theodore Gray, he has filled that plexiglass, or maybe it's just glass. I don't know. It's filled with sulfur hexafluoride. And so he made a boat out of aluminum foil. You see, he's just taking it with a ladle and scooping it up. And because sulfur hexafluoride is kind of heavy. So, and now he's gotten his aluminum boat to sink. So it's just, like I said, you can see it floats on top by buoyant force. So, and we do have a fairly, I don't know, say nefarious use for sulfur hexafluoride. It's part of our stealth technology. So, has anyone ever seen a stealth plane before? Oh, you have. Which one did you see? Well, you can see they fly around Oahu all the time. No, the Raptors. They fly those all the time on Oahu. The F-22. You never.
You mean like the YouTube plane,
Oh yeah, no, I've seen that, but that's not stealth.
the Blackbird?
The Blackbird, yeah, that's not stealth.
Oh, not that.
No,
Okay. Then, no.
yeah. I guess we don't live in Oahu. They fly those all the time on Oahu. I mean, they have.
You talking about the F-22?
Yeah.
All those are stealth.
Yeah.
They like what makes it stealth, like just the radar, like they like radar or something?
Yeah, what makes them, there's three things to our stealth technology. So if you look at not so much for the Raptor is really smooth, but if you look at the original, like the stealth bomber and the first stealth fighter, they have really angled edges on them. And how radar works, you have your plane or whatever flying, and you shoot the radar, use microwaves, and then it bounces back from the whatever aircraft you're looking at, and you have a detector, and you just ping it, kind of like just almost like, if you know how sonar works the same way. You shoot it, it pings, comes back, and then you can figure out your object where it's flying.
But when it pins back, that's when you do mission.
Well, that's the other thing with stealth technology. It absorbs the microwaves. First one is they have the angles on it, so when the radar comes, it deflects off of it. So it pings, but instead of going back to the detector, it just goes off in a different direction. So it pings the wrong way. That's number one. Number two, the material absorbing it just absorbs the microwaves. And the third thing is I mean, if you get the jet to absorb all the microwaves, but then it has a big smoke plume coming off the back of it. Actually, most radar, you find what's called the heat signature. It's the exhaust from the jet. And so you have to have a very low heat signature going. If you heard a heat-seeking missile before, heat-seeking missiles, they don't actually seek heat. They seek the exhaust. So it's a radar. It's actually a radar guided missile. It's not a infrared guided missile. It's a radar missile. So the heat seeking looks for the engines. And so that means the engines have to, specifically, they have to have very clean combustion and have no soot. And one of the ways you can do that is to make sure that there's no free radicals. And one of the ways to make sure there's no free radical is the halons, right? So we put sulfur hexafluoride in our fuel for our stealth fighters, helicopters, and that kind of thing. And so I remember, if you ever look at the pollution, I guess I haven't been following the latest climate summit, but if you look at some of the summits, they're like, oh, and here's the levels of sulfur hexafluoride. You're like, what do you have to say about that, United States? You know, because it's basically all from us, from flying our jets around, because stealth, because you don't see them on radar, you can put stealth on really long missions, and and you don't need to have big escorts. So you just send the stealth fighter or bomber and deliver the payload and fly back home. So there's sulfur hexafluoride all over the world, thanks to good old USA. But All right, so here is one. So writing Lewis structures. So more things you learn. Write the Lewis structure for xenon difluoride. And again, you know, like it's a noble gas. Noble gases actually can bond. So the way you do these can anyone guess the number of valence electrons for xenon? No, it's not 0. It's 8. Plus 2 times 7 for fluorine. So that's going to be 22 electrons. So xenon difluoride is 22 electrons. You put the big atom in the center, put the fluorines on the end. So we have 4 electrons placed, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. So placed all the electrons. We put octets on the outside, put the rest of the electrons on the inside. And if you look, xenon actually does have an expanded octet. Fluorine is not going to have expanded octet because it's period 2. I mean, period 3 and beyond. Xenon is period 4. And you can see here, so I'm sorry, it's 5. Whoops. So xenon is down here, and it has 8 valence electrons. So, like so. And later on, next chapter, we'll talk a bit about this. This molecule is actually linear, and all the electrons go in what's called the equatorial plane there. So you have all the electrons all coplanar along the centers of the electron density, at least coplanar in the xenon. So do you see how to write that? It's reporting back. I was talking about stealth fighters. Reporting back to Big Brother for me. I'm joking, of course. So, but do you guys see how to do this, or is it okay? Oh, right. What? Example? You want more examples? Oh, I got one coming up. Actually, I was thinking about ahead. I might do a kind of a classroom activity where I do a lot of Lewis structures. So I might do that. I'm just wondering about the Wednesday before Thanksgiving, because you're gonna probably be all really tired anyways and want to do something that's almost, because you remember back to grade school when, you know, the day before holiday was always going to be, you know, something fun. So I'm thinking about doing that. So anyways, why, you want to do an example? I can pull one out of the air if you like. Okay, so one of the ways, so if you want to guesstimate, get an estimate on certain chemical reactions, one of the ways you can do is look at the average bond energies and seeing about the bonds broken and bonds forming. So if you look at like a bond, so someone like here is the molecule for ethanol. And so when I look at this molecule here, I see this oxygen here. Oxygen is going to be electronegative center, and it's going to draw electron density here, and also a little bit more from here. So it's an electron vacuum cleaner. So it's going to suck a lot of electrons towards itself. Actually, this carbon-hydrogen bond is going to be easier to break than this one here. So because this oxygen atom here is drawing a lot of electron density to itself, and it's going to draw electron density away from this hydrogen, and the electron poor hydrogen is actually going to be easier to cleave this bond than that bond here. That's another carbon atom away. But what you can do though is take a bunch of molecules like this, and you can average up all of the carbon hydrogen bonds, how much energy it takes to break the bond. You can come up with in average bond energy, and it was decided upon to have 414 kilojoules per mole. So what do I mean by that? So the bond energy, it's the amount of energy you put in a bond to break it, or you can look at it as the amount of energy that's released when a bond is formed. So, and a very kind of cheeky example, well, the more electrons you share, the harder it is to break the bond. So if you look at the nitrogens here, see here's nitrogen single bond is 163 kilojoules per mole, 418 for the double bond, 946 for the triple bond. So it's kind of like imagine like a friendship, you know, or something like that. If you just met someone, you know, like, oh, you know, I met my friend here in the chemistry class. We're bonded, you know, it was a nice experience, you know, but it's, you know, it's okay. You know, we're not super close, but we're kind of close. Like, what if I gave you $163 to never see that person ever again? You're like, fine, you know, that's cool. Let's say you like met in chemistry class, but then you're like, you know what? We're going to move in together. I think this is going to work. We're going to be friends and we're going to live together. And we actually bought a car together. You're like, okay, $163 to break up with this guy. Like, no. How about 946? Okay. Right. So, right. Everyone has a price. The nitrogen triple bond is 946 kilojoules per mole. So nitrogen triple bond is triple bonded. So it's a pretty strong bond, but it's not the unbreakable bond. It just takes a lot of energy to break that bond. And so that's how much it's to break. It's also how much energy is released when it forms. So when the nitrogen triple bond is formed, it releases that much energy. So you can look at it either way, breaking it or forming it. So, and then the heat of reaction is going to be the number of bonds broken. So that's positive enthalpy minus the number of bonds formed. And so it's releasing the energy. So remember, positive energy is going into the system, negative energy is leaving the system. So that is where this comes into play. And it ties directly back into Lewis structures. So let's do an example of this. Hydrogen gas can be made by reacting methane with water. And I was really proud of the textbook because this is one of the few times that this is something that we actually do. We actually do make hydrogen this way. So hydrogen is not typically made in other ways. But this is how we get hydrogen industrially, at least. Well, the other way we get it is from reforming molecules to make gasoline. So you can cyclize molecules and then hydrogen pops off for that. So that's the other way we can get hydrogen. That's more of an accidental way. Okay, but steam reformation. And what is using the average bond energies, calculate the heat of reaction. So let's write the Lewis structures. So for methane, carbon has 4, hydrocarbons are pretty easy. Carbon has 4, hydrogen has 1. So we have 8 electrons, we have 4 lines. We're actually done already. That one's pretty easy. So then we have water. So oxygen has 6 electrons. Hydrogen has 2. So, well, 2 times 1, 6. We have 8 electrons. We've placed 4, 6, 8. So water's done. And I'm just going to go ahead and copy that to show you where the bonds go. And then hydrogen. So hydrogen. It's only one choice. They share 2 electrons. I'm not going to copy this. I'll just write 4 times. And carbon dioxide, we've done this one before. So we have oxygen double bonded, carbon double bonded O, and just 1. Okay. So let's look at the type of bonds. And we have 4 carbon hydrogen bonds. 4 carbon hydrogen bonds. And different color. I'll do blue for water because water is blue, right? It's not.
It's actually clear, but
It slightly absorbs in the red. Sure. We have 4 oxygen, hydrogen single bonds. And then what should I do for hydrogen? I'll do green. So we have 4 hydrogen bonds. And then we have 2 carbon double bond oxygens. Oops. So right. So everyone see there that we are breaking 4 carbon hydrogen bonds, breaking 4 oxygen hydrogen bonds, forming 4 hydrogen single bonds, forming 2 carbon double bonds. Yes.
the book says something about an exception for CO2. The bottom.
Right here. Yep. Right in the chart. Glad you read the book. Awesome. Okay, so remember, positive bonds broken, negative bonds form. So bonds broken. So just written there, it's going to be 4 carbon hydrogen bonds plus 4 oxygen hydrogen bonds minus the quantity 4 hydrogen plus 2 carbon, bond O, and specifically CO2. And then you look at the chart. What is carbon hydrogen? Carbon hydrogen is right here. It's 414. 4 times 414 plus 4 oxygen hydrogen. Oxygen hydrogen. Oh, it's down here. 464. 464 minus, bring this down. For hydrogen, I shouldn't write hydrogen. I should look up hydrogen. Hydrogen is that 436? Yeah, 436. 436 plus 2 is 799. Is that what it was? Yep, 799. Okay, and extreme level of laziness, I'm going to go ahead and look up. Chapter 10, near the end. Okay, and doing that, it's positive 170. So do all this is 170 kilojoules per mole. All the units on that are, I'll just go ahead and emphasize the positive sign. Okay. So from this, so why do we care? Imagine you're the chemical engineer running this, and you know, like, what's going to happen to this reaction vessel? And I know, oh, this reaction vessel is going to get cold. So because it's endothermic, it's going to require energy. So I'm going to have a heat source near this, a flame or heat exchanger, something like that to get this reaction to keep it going. So does this make sense? All right. And you want an example, you got one. What is the heat of formation of ammonia from hydrogen-nitrogen based off the bond energies? And I've gone ahead and given you the Lewis structures of everything. So now let's see if you can figure this one out. like I said, it's going to be sum of the bonds broken minus sum of the formed. Sum up the broken, subtract the sum of the formed. I just got an ad for Ralph's. There isn't even a Ralph's here, and is there even Kroger here?
I get so many ads for California.
There's a pretty heavy hint. All right, I think it's A. I think it's B. I think it's C. Okay, so you think it's C?
Fun.
Almost everyone's going for B. So yes, B is are you guys following it, or is it, okay. Okay, yeah, because it's gonna be 946 plus 3 times 436 minus 6 times 389. The 6 bonds there, and you do that, you get negative 80 kilojoules per mole. So everyone got this? All right, and next thing we're going to talk about is the average bond lengths. So generally speaking, the more closely bound you are, the closer you are. So and this works for your friendships too. So so what do you do if you haven't seen you have an acquaintance, and what do you do when you haven't seen the acquaintance for like 2 months? How do you guys interact? Fist bump. Yeah, we can do that. That's fine too, right? You fist bump. What do you do when you see your childhood best friend who you haven't seen for years? What's gonna happen? This one, okay. All right, maybe someone you're really close to, parent, sibling, partner, I don't know. How do you greet the person? Yeah. Actually, yeah. I mean, you even say that, like, this is my classmate, that's my acquaintance. Or this is my blank friend. How would you describe a friend? Your close friend, right? And your close friend because like, this is my close friend. See, we're actually close to each other by proximity. So it makes sense. It makes sense that we're close friends because we're standing right next to each other. We're close, right?
My chemistry friend.
Yeah, all the way over there. Not too close. Yes. So same thing with bonding. So you look at carbon and the bond length. This is the average distance between the nuclei. And I say average because it vibrates. But the average distance between a single bonded carbon is 154 picometers. But as you can see, when it bonds more closely, the carbons get closer together. So when they share more electrons, so here's 2 electrons, 4 electrons, 6 electrons. So they get more bonded and they're actually closer together. They become closer bonded. So generally speaking, when things become more bonded, they become closer. And also, you can see the bond strength here increases. So single bonded, it takes 347 kilojoules per mole. And then for triple bonded, 837. So it takes a lot more energy to break apart a triple bond than a single bond or double. Yeah, question?
Did you do me a favor?
Oh, what's that?
Could you draw tiny smiley faces on the electrons?
Which electrons?
All of
The electron clouds, okay.
them in black pen.
We love you.
Okay, there you go.
Thanks.
All right. It's what?
It's helpful for it.
Okay. I'm glad it's helpful for your education. If that's easy enough, sure, why not? And but this is what is chemistry unless I say something and contradict myself, right? If you look at the nitrogen halides, so you can see that there is no trend here. It doesn't make any sense. I mean, the carbon triple bond makes perfect sense, or the carbon bonding, but then you have the nitrogen halide bonds, and you can see that the bond length increases. So you're like, oh, okay, well, the bond length is getting longer. We'd expect the strong strength to go down. That makes sense. Actually, no, wait, sorry. If the bond is bond length is smaller, you expect higher energy. You're like, wait a second, that broke that trend there. And you can see here that just because something tends to be true doesn't mean it's going to be true for everything. So there's exceptions to the rules and exceptions to exceptions. So, all right, and then we were done with this chapter. We only have one more chapter to go. And actually, I did want to get through a lot of, believe it or not, I didn't want to get through all of chapter 10 before Thanksgiving, but I wanted to get through some of it up till we talk about polarity of molecules, because like I said, I wanted to do some examples. And I do want to caution you, time's gonna go fast. So I've noticed that. Do you guys feel this way? I guess you're like right when you start hitting the holidays, shoot, time disappears. So time is gonna start to disappear. There's less than a minute left. Anybody have any questions or anything? Okay. All righty then. You guys doing okay, Zoom? No one said anything. You're so mesmerized by my amazing chemistry presentation. You were speechless. Did you like the smiley
Yes.
faces on, you like the smiley faces on the electron clouds? Okay, yes, okay. It's going to be hard to write smiley faces on all electron clouds though. But okay, I will go ahead and stop recording.